Okay, let's go ahead and take a quick look at this problem. I know we already reviewed it, but I do want to get it on the video. So when we know that the mole fraction is 0.450, the easiest way that I found was to assume I have 1 mole total, which means I have 0.450 moles of benzene and 0.550 moles of carbon tet. Then using the molar masses, I can change them each into grams and calculate percentage. Grams of benzene divided by the total grams times 100, we get the percentage. Okay, I just wanted to get that on the video. So now, when we look at all of these concentration units that we've been using, we can also think about solubility, and in a different sort of way. We can say, does this dissolve? Yes or no. It's not soluble. You learned in your introductory chemistry classes to say this is soluble, this is not. Then in Chem 111 you learned, I hope, to say, well, we were only kidding in intro. It's not really insoluble. It is sparingly soluble. A little bit dissolves, but for now we'll just roll with insoluble. Now in 112, when we get into equilibrium, we are going to say it is sparingly soluble, and we can actually calculate the solubility. We'll be doing that a little bit later. But the definitions we want to work with for now are saturated, unsaturated, and supersaturated. When you have a saturated solution, you can tell that it's saturated because you have solid sitting at the bottom. And you have solid going into solution at the same rate that it is coming out of solution and precipitating. When you have an unsaturated solution and you look in the beaker, you just see the solvent because you can't see what's dissolved. And you can dump more in and it will dissolve. And when you have a supersaturated solution, you have exceeded the solubility amount, but it looks exactly like an unsaturated to your naked eye. Now the difference is if you add a crystal to an unsaturated solution, it will dissolve. If you add a crystal to a saturated solution, it'll go sit at the bottom. And if you add a crystal to a supersaturated solution, it'll provide a nucleation site, and everything in here now will just precipitate, and you'll just have a big blob of solute. Everything falls out. You will precipitate more than the excess. You'll almost precipitate everything in there. So that's revisiting the definitions. I think you should have discussed this previously in your introductory or your first semester Gen Chem class. So now we're going to just keep those ideas in mind so that we know what we're talking about later on. We're not going to do anything with definitions right at the moment. What we want to talk about next is a type of property that is called a colligative property. Colligative properties are properties of solutions, and they're kind of unusual because they depend only on what number of particles you have, how many particles are dissolved, not what the particles are. If you have different kinds of particles, but the same number of them, you'll have the same effect on the solution. So we talk about two vocabulary words, volatile and non-volatile. Volatile means the compound evaporates under the conditions we're working with. Non-volatile means it doesn't. So water is volatile at room temperature. If you leave water sitting around, it will evaporate. Okay, lead is not volatile. It doesn't evaporate. Sodium chloride is not volatile. It doesn't evaporate. We figured that out in lab last week, right? Or earlier this week. So we can also say things like hexane is more volatile than water because hexane evaporates faster than water at a given temperature. So now we're going to start looking at the effect that we have of solutions of non-volatile solutes. Liquid solutions that are made from a non-volatile solute have a lower vapor pressure than the pure solvent. Now in Chem 111 you were introduced to the concept of vapor pressure, and you know that vapor pressure is the pressure that the vapor of a liquid has at equilibrium in a sealed container. If you have a bunch of molecules in here, and they're molecule X, this is our solvent. If I seal this container, these will start to evaporate, and there will be some pressure above the liquid in that sealed container, and that's called the vapor pressure. And you remember from Chem 111 that we need two things for a molecule to be able to evaporate. What two things have to be in place for a molecule to be able to evaporate? It has to have energy, right? And it usually is heat energy, but we think of it has to have enough energy to break away from the solution. So it has to have enough energy to break all the intermolecular forces and be able to escape. And what other thing has to be in place for that high energy molecule to escape? This isn't a secret thing. This is a real obvious thing. Look how I drew these molecules. Where are they? At the top. Can this molecule evaporate? No, it can't get out, right? So they have to be at the surface. So they have to be at the surface to evaporate, and they have to be moving fast enough to break away. And there's only a certain percentage of molecules that can break away at any point in time. And as you raise the temperature, you get a higher percentage of molecules that can break away. So now let's think about a solution. A solution is different than a solvent. The solution is different because you have solute mixed in here with the solvent. So here's my solute molecules. So when I mix these in, my solute molecules are occupying some space at the surface. So when I look at this, what's going to happen to the vapor pressure when I have fewer solvent molecules at the surface? Do I get the same rate of evaporation here as here? It decreases. And the reason it decreases is because I have fewer molecules at the surface, so fewer molecules are going to be able to evaporate. Let's say at this temperature, 20% of the molecules can evaporate at the surface. So 20% of these can evaporate. But now I've only got 4 molecules here, so 20% of those can evaporate, so the vapor pressure goes down. So that is a colligative property. And I brought something to show you to set up a demo to try and visually see something about colligative properties.